I'm originally from Romania, but I lived for 10 years in Canada. I did my PhD there and then a postdoc, and now I live in Belgium. So
where in Romania?
In Arad, it's the western part, so it's like 50 kilometers from Timișoara.
I was in Romania yesterday.
Huh?
I was there for a wedding, my wife. It's Romania. I was in
really? Okay.
Salaj area.
Salaj, yeah. It's a beautiful region. Sure.
This is not working.
Yeah.
Hello, welcome back. So welcome to the second fringe session of the Graphene Week. This session will be dedicated to success stories from the partnering division of the Graphene Flagship. The project Graphene Flagship is not a standalone, but was planned since the start to interact and to collaborate in a synergic way with lots of other initiatives, lots of other projects. So besides and beyond the core projects, we have a continuous collaboration with funding agencies at national level that through so-called flag year call also fund different kinds of projects. And today we will see some very nice examples of how this collaboration is going on, which kind of research was performed in this first phase. So I will not waste other time, and we can start with the first talk that is from Lucian Kovacci from the project Trans2D TMD. Please.
Okay, thank you very much. Thank you for the introduction. Also, I would like to thank the organizer for giving us the opportunity to showcase our results in such a beautiful setting, but also for such a distinguished audience. So, my name is Lucian Kovac, and I'm the representative for the Trans2D TMD project, which is coordinated by University of Antwerp. So let me just briefly start by just giving you a brief overview of the scientific objectives of our project. So first, we're trying to investigate the electronic properties of metallic transition metal dichalcogenides, either by intrinsic doping or by inducing a topological surface or interface states. But then on top of that, we were interested to seek new two-dimensional materials as alternatives to graphene with tunable properties such as optoelectronic properties, but also tunable spin degrees of freedom or spin transport, and also novel topological properties. Last but not least, we are interested in developing novel theoretical methodologies and software that can be used by people like you, hopefully. And our interest here was to be able to describe large systems with experimentally relevant sizes and disorder, or types of disorder, but also software that can use ab initio inputs, and then this should be accurate, highly efficient, and user-friendly. So because I don't have too much time, I will just focus on these two topics today. Before I continue with presenting the results, let me just briefly introduce the Trans2D TMD network. So the project is coordinated by Professor Peters at the University of Antwerp, and is funded by the Flemish Science Foundation. And then we have another full partner from Germany, Professor Heine, of course funded by DFG, and of course co-funded by Flag Era project. But then we also have associate partners from Netherlands and from Spain, and Professor Seifert from Germany also, which is also part of the core graphene project. And I just list here some collaborators, which are both from the core project and from outside the project. So let me just continue now with the outline of the remainder of the talk. So as I said, this will just be some selected results. And the first part will be on some predictions of novel two-dimensional materials, which here I will just present some example of anisotropic 2D material, some examples of materials with high carrier mobility, and also low enough gaps that, so that they can be used for optical applications. And then some interesting results. I will show you a material which shows the double Dirac point. And in the last part of the talk, I will introduce these new theoretical methods and software which are order of n tight binding approaches which use spectral methods and Chebyshev expansions, and I will just present these two types of two softwares that we have developed. So to just continue with some examples of types of calculations that we have done in our project. So first of all, we wanted to look at this interesting material, tungsten ditelluride, which of course is a two-dimensional transition metal dichalcogenide, but different from the usual ones which show the H phase and are semiconducting. This tungsten ditelluride has the lowest energy phase as a T phase, but it's a distorted phase. And because of the dimerization of the tungsten atoms, you have a very anisotropic situation, which shows up in mechanical and optoelectronic properties. So, for example, to start with, just the equilibrium configuration, so this material is semi-metallic, but it can be transformed into a semiconductor with just 1% strain. And interestingly, because of the anisotropy, if you apply strain in the different directions, like parallel and perpendicular to the tungsten dimer, you have either appearance of a gap or a shift of the two bands. And optical properties also are anisotropic. So here I just show the imaginary part of the electric function, which is shown here as a function of the amount of strain and the direction of the response. So there is some anisotropy in the direction of the response, but also in the type of strain. So for example, here these results are shown for strain perpendicular to the dimer, while these are shown for some strain which is parallel to the dimer. So this material has been also shown to be a superconductor and has anisotropic magnetoresistance, so therefore it should be a very interesting material for applications. A different type of calculation where we were looking for high carrier mobility, and such an example here is on germanium triphosphate, which in the bulk form was known and synthesized already from 1970, but the cleavage energy is just 71 milliV per angstrom square, which is, let's say, maybe a double or triple than graphite, so it's not that large, and one could think that this could be exfoliated. So basically, the structure of this material is still this puckered honeycomb lattice, where every fourth atom, germanium, is replaced by phosphorus. And so the bulk is metallic, but due to strong confinement, as you thin it down to mono or bilayer, you start developing a gap. But the values of the gap here, the gaps are very interesting for optical applications, because the response is in the visible range. So this should be a very interesting material for photovoltaic applications. But also, interestingly, they show high carrier mobility for monolayer. So you can combine, again, this high carrier mobility with small gaps, which in principle, you have such properties also for phosphorine, but as we know, it is highly reactive unless you encapsulate it. So this could be an alternative material. Another such example is, again, transition metal dichalcogenide, but the phase here is neither the H phase or the T phase, but it's the so-called S phase, which actually has slightly higher energy than the T or H phases, but is still stable. So it's interesting to look at its properties, because one can maybe achieve these metastable states experimentally. So we have shown that, again, this is very interesting for optical applications, because it has the band gaps on the order of 0.5 to 1 electron volts. So as you replace the chalcogen atom with sulfur, selenium, or telluride, the gaps remain more or less of the same order. And I will just skip this point for now due to a lack of time. So another interesting material is this thallium-2, selenium-3, which is again a highly anisotropic material, which could be exfoliable. But if you look at the electronic properties, you see that you have this band crossing, which actually looks exactly like a double Dirac point. So if you zoom in around this point in the band structure, you'll see that you have highly anisotropic Fermi velocities, and you have these double Dirac points. And interestingly, when you add spin-orbit coupling in the calculation, there is a gap forming, and therefore this makes it an interesting material for topological applications. And again, this can be tuned by strain, and the response to strain is highly anisotropic. So let me now switch gears and explain the types of softwares that we have developed. So we are interested in tight binding tools where you want to bridge the gap between some solid states type of models or calculations and nanoscale models. And these are tight binding Hamiltonians, which can use input from ab initio, but are still amenable to large system sizes. So we are just trying to push as far as possible into mesoscale dimensions. So that is the challenge, to go from nano to mesoscale. And an additional challenge for 2D materials is the fact, as shown in the previous slides, you can end up with a pretty complex unit cell, which it turns out that this translates into a complex number of orbitals or complex Hamiltonian. And in addition, if you have hybrid materials, you end up with large unit cells. For example, we saw today that and yesterday, that if you have these Moiré unit cells, that you have pretty large unit cell. So our solution to this is the software so-called we call Kite. And this is a high-performance quantum transport developed in collaboration with João Lopes, Iris Ferreira from York, and Tatiana Rapaport from Rio de Janeiro. So the main challenges for such a software are first that you want an accurate type of calculation. And here we solve this problem by using Green's function evaluations by the means of real space polynomial expansions. So then you can provide the fine control over the accuracy and the resolution for both pristine and disordered system. But you also want a scalable and fast simulation. And that we have solved by using some state-of-the-art fast and scalable algorithms, mainly using some efficient domain decomposition where you can take advantage of CPU clusters. And another interesting challenge is the versatility. So you would want to have a software that does some generic type of calculations, so generic equilibrium or out of equilibrium properties like densities of states or optical conductivities or nonlinear response. For any kind of system, from complex molecules to solid state systems with large unit cells. And you also want it to be user-friendly, and for that we interfaced with one of our previous programs called pipe binding, where it's very easy to define and import tight binding models. So just a brief introduction to spectral methods for people that don't know, and this is our approach to have accurate and with fine resolution calculation. So any target function, of course, you can expand in a set of orthogonal polynomials, where here x, it's a real variable, is the energy, and it's defined, of course, on a finite interval because you have a bound spectrum. So now the question is, what kind of basis set can we use? In principle, you're free to use any orthogonal set of functions, but you can find out about this. You can go ahead and read this very interesting book by John Boyd. So he has this moral principle that when in doubt, use Chebyshev polynomials, unless you're very sure that another set of basis function is better, then use Chebyshev polynomials. Unless you're really, really sure that another set of basis function is better, then use Chebyshev polynomials. But there might be, let's say, a case where you have some periodicity in your system, where, of course, you can use then Fourier expansions. But these functions, as I said, the x variable is the energy, so there is no periodicity in such functions. So yeah, these are the famous Chebyshev polynomials that we're going to use. And the nice thing about orthogonal polynomials is that they have a recursive relation between polynomials of different orders. So then if you evaluate some moments of these expansions, these are just some matrix elements of polynomials of different orders. So for example, this first order would be some density of states, then conductivity would be second order. And this would be the number of operations that you have to perform. And we have shown that this is highly stable and uniform resolution. And you can use it for general purposes. So in the interest of time, I will just keep this. Of course, there's a lot of history behind this. And we have just recently come into the field, and we've used these methods in our software. And there's a very nice interface where you can easily define the unit cell and then set up the system as you like, kind of similar to this quant software package. But we use that interface to build the model and then define the disorder. That is fed into an HDF5 system for input-output, and then this is fed into this C++ code, which does the bulk of the calculations, and then there are some post-processing tools that we use to extract the functions. So this is a set of a type of calculations that are available. So right now we are in the pre-release phase, so you can find, or beta phase. So the ones that show here a beta availability, you can already go on our website or on GitHub and download this code and play with it. So we can do already a linear response function, DC, AC conductivity, either transverse or longitudinal. You can do linear response functions with very high resolution, and these are the type of dimensions that we can solve with our system. So in the interest of time, I just want to say that make it short, and want to say that the important part here is that this is an open source code, and you are free to contribute, and we would be happy if such a code can pick up and everyone can contribute. So I will end up with acknowledgements. The people in the different teams, people in the Kite team, and the funding agencies, and also our collaborators in the core project. So thank you very much.
Thank you. Let's hope that lots of people will use this code. We have time for 1 or 2 questions. Yes? Wait for the microphone, maybe, so everybody is coming from there or from here.
So do you take into account whether those materials that you look at can be synthesized and what boundary conditions would be for that? And second part of the question would be, how do you deal with imperfection? Like if you have like antisides in there and...
That's related to the first part of the talk.
Yes.
In principle, yes, you have to think about whether these are, for example, layered materials and you can separate the different layers. But you also want to push the boundary to kind of predict what people should look at, whether it's synthesizable or not, that remains to be seen. But at least if you have information about the possibility of peeling different layers, so making very ultra-thin materials. And then imperfections, of course, at DFT level is not very easy to take into account. But if you want to talk about response functions, then that's the reason why we developed such a software where you can devise a model of the different types of disorder. Because so there's a problem with tight binding models that you have to model the pristine system, but you also have to carefully model the defects. So, but once that's kind of a separate issue. Once you solve that, you can feed in this kind of software to do the simulation.
Thank you.
Okay, unfortunately, we have a very tight schedule, and we use part of the time for the questions for the talk. So let's thank Lucian again, and we move to the next speaker. The name of the project is H2O, heterostructures of UV materials and organic semiconductor nanolayers.
Francesca, thank you very much for this introduction, and I would like to thank the organizers of this session for offering this opportunity to present our recently launched project, which is called H2O and stands for heterostructures of 2D materials and organic semiconductor nanosheets. You see this consortium of 4 organizations, the University of Jena with 2 PIs, Anthony George and myself, with Ludwig Maximilian University of Munich, led by Bert Nickel, and also with Chalmers University of Technology. The group are represented by Sergei Kubatkin, Saraj Dosh, and Samuel Avila, and with the University of Twente with Michael de Jong, who is leading the activity. You can see all these gentlemen, or most of them, during our kickoff meeting very recently in Jena. And before presenting or introducing you to our project, I would like to say a couple of words about Jena. Jena is a university, old university city in the middle of Germany, and this is a home place of about 25,000 students, and also 10 research institutions with Max Planck Institute, Leibniz Institute, Fraunhofer, Helmholtz, DLR, which makes a very viable environment, research environment in this area, and Jena is also represented by strong optical industry. Kite is a company which everybody knows, and established already by Ernst Aber, Otterschott, and Kite. There is a strong interaction always in Jena between the research institution, between the academic research and industry. This slide should introduce you to the goals of our project, what we would like to do. We would like to combine these different 2D materials, graphene, carbon nanomembranes, which are molecular nanosheets, TMDs, with a new material which we recently developed, that is nanosheets of organic semiconductors. You can ask the question, why organic semiconductors? And there are quite good reason for that. First of all, organic semiconductors fair low-cost technology. These organic semiconductors are compatible also with flexible electronics. The temperature processing temperature is quite low, and also the properties of these materials can be chemically tuned. What is last but not least, that organic semiconductors is already commercialized technology with a lot of important products on the market, like displays, like solar panels, or like lightings. In these different materials which we would like to implement in our devices, 2 materials are made by unconventional material synthesis. This is carbon nanomembranes and pentacene sheets, and this synthesis is based on electron beam-induced chemical reactions in soft matter. And at this place, I would like to make you a little introduction, because I can imagine that not everybody is aware about such kind of processes. If you speak very roughly, you can divide the electron and molecule interaction in 2 parts. The interaction with high-energy electrons and the interaction with low-energy electrons. The high-energy electrons, the electrons are in the range of kiloelectron volts, 10 kiloelectron volts, or 100 electron volts. In this case, the electrons are interacting directly with atomic nucleus, resulting in displacement, and can introduce in this way certain chemical reactions. In the case of low-energy electron, the interactions is more with the electrons in the valence band, and different process can take place, which is represented here by these chemical reactions, which finally results to the synthesis of new materials. And some examples of the materials is given here. For example, recently we have shown that by employing high-energy electrons, you can generate graphene nanoribbons inside the carbon nanotubes, for example. I give you this example a little bit more detail. And low-energy electrons we use for generation of carbon nanomembranes and organic semiconductor nanosheets. let's stay by this first example. In this first example, you see this collaborative work between 4 groups, between Andrei Chlobostov and Jena Bestland, University of Nottingham, between Ute Kaiser, my group at the University of Jena, and also the groups of Klaus Mühlen. So in this case, carbon nanotubes have been filled with such hexabenzocaronan molecules, and you can see from this high-resolution transmission electron microscopy images how perfectly they are ordered there in such a carbon nanotube. If you start to irradiate these carbon nanotubes with electron, you see some transformation. If you follow this transformation very precisely, you can see that these individual molecules are fused together, forming a graphene nanoribbon, which can be then imaged here. This is example for this interaction of high-energy electrons with matter. Low-energy electron, this is another example where we are working now for quite some time. This is conversion of organic aromatic self-assembled monolayers using this template-induced synthesis into the material what we call named carbon nanomembranes, which are basically molecular nanosheets. By making a self-assembled monolayer on such a surface, you can again, by radiating the structures with electron beam, can result in the cleavage of carbon-hydrogen bond and fusing of these molecules with each other and synthesis of such carbon nanomembranes with only 1 molecule thickness. In comparison to, in contrast, for example, to the synthesis of graphene nanoribbons, where you use transmission electron microscopy for synthesis of such materials, you need a fairly simple equipment, which you see here. This is the reactor in my research group. This is vacuum chamber. This is electron flung guard installed here, and actually ampermeter. This is only the case what you need for such kind of electron beam induced chemistry. The materials formed are shown here. This is an example of carbon nanomembranes of some solid substrate. You can stack these materials in the thicker layers. You can make these materials freestanding. Actually, with these carbon nanomembranes, you can do any kind of microfabrication as you do with any other materials. I could speak about this hours because it's really very interesting material. I would like to point out only 3 properties. This material dielectric, this is soft matter, which makes a lot of attraction for application in biological application, and these materials can be perfectly chemically functionalized for the purpose of your experiment. How far you can go with this electron beam induced synthesis? There are a lot of talks and there's a lot of work at present on synthesis or assembly of vertical heterostructures, but there are not so many talks on the synthesis of lateral heterostructures because due to some fundamental problems. You can overcome, at least in some cases, this problem by again inducing electron beam induced chemical reaction. As is shown schematically here, you start with a graphene sheet. This graphene sheet can be patterned by lithography. Then the free areas of graphene can be filled with molecules by electron-induced irradiation with low-energy electrons. You not only cross-link the molecules with each other, converting them into carbon nanomembranes, you also introduce stitching between the edges of the graphene ribbons or graphene any structure, put it this way, and carbon nanomembranes. This is the example, for example, this matrix of dielectric carbon nanomembranes where graphene ribbons are incorporated inside. This is graphene dots inside the dielectric carbon nanomembranes. So these materials have very different mechanical properties. That's why you can, in lateral force measurements, you can very well recognize wide graphene areas and soft carbon nanomembrane areas. This is a graphene SEM image of graphene ribbons and carbon nanomembrane ribbons, and this is a matrix of graphene with such dots consisting of carbon nanomembrane. These heterostructures form a very sharp atomic edges, and this is I would like to demonstrate you on another example. This is now the heterostructures between carbon nanomembrane and molybdenum disulfide, where you again use CVD grown molybdenum disulfide. You fill the free areas with respective molecular precursor, and then you cross-link this is with an electron beam. And if you start to analyze how sharp atomically sharp other edges of these materials. So you will see with this high-resolution transmission electron image acquired in the group of Ute Kaiser that they possess nearly atomically sharpness. You can see very well this grain boundary between the short-range ordered molecular carbon nanomembrane and very well ordered molybdenum disulfide. Now we are coming actually to the topic, giving this background of electron beam-induced chemistry. I would like to show how you can apply it to make new two-dimensional materials out of organic semiconductors. The idea is presented here. So actually, we use the property of low-energy electron that penetration depths can be precisely tuned depending on the energy of the electrons. So therefore, if we, for example, make a thin layer of organic semiconductor, we can cross-link only the topmost layer of this film without preserving the whole crystallinity of the remaining film. And this depth of penetration of electrons can be tuned here down to 5 nanometers, which corresponds in case of pentacene molecules only to 3 atomic layers. And in this case, the such waste, this cross-linked layer works like a carpet backing, stabilizing the whole system. Stabilizing the whole system and enabling to make a new kind of nanosheet of this organic semiconductor. You see the example here, organic semiconductor sheets floating on top of the water. You don't need any stabilizing layer like PMMR, which you use for other two-dimensional materials because this film is enough stable. So if you zoom in, for example, on such a sheet, transfer it onto a solid substrate, you can recognize this faults, which is a signature that is sheet material. And if you zoom further in, you can recognize a typical terrace-like structure of pentacene, which is completely preserved here. This is example of transfer the sheet onto the device structures, and this is freestanding 2 millimeter in diameter pentacene membrane on top of such a brass hole. So we studied really this process in very detail. This is summary of spectroscopy data where you see, depending on the electron beam energy and depending on those, we can tune the thickness of this cross-linked layer very well. And finally, to convince even ourselves that the material still consists of the stabilizing top layer and perfectly crystalline rest. We, in the group of Bert Nickel, very detailed measurements of specular reflectivity, X-ray specular reflectivity, and X-ray grazing incident X-ray diffraction have been conducted, which confirmed that in this way we can stabilize the film by introducing this cross-linked layer on the top, which is only 3 nanometer thick, and with preserving perfect crystallinity of the remaining pentacene sheet. And this is, of course, the interesting question, how well this organic semiconductor work in devices. This is a comparative analysis of one pentacene sheet, which was strongly cross-linked into the depths, and pentacene sheet, which was cross-linked only on the surface. And you can recognize that with this surface stabilization, there is practically no difference in field effect characteristic between the pristine pentacene sheet and the pentacene sheet produced by this cross-linking and transfer, and only if you go to the higher electron energies and higher doses, you introduce some damage. If I'm not mistaken, I have 6 minutes still.
Yeah,
I'm sorry. Because
you're right.
Okay, so I would like to point out here a very important point with organic semiconductors. They're very challenging to grow organic semiconductors on target substrate due to different substrate molecule interactions, which are maybe not favorable for epitaxial growth and so on and so forth. And I would like to show you some examples. This is, for example, how in AFM pentacene film looks if you directly evaporate pentacene of prefabricated gold contacts. You see very big difference between the morphology of the pentacene on gold contact and the morphology of pentacene film otherwise. If you transfer the film on the prefabricated contact, the pentacene film grown on PVA layer, you see that the morphology everywhere is the same. And this is you clearly detect also in device behavior the contact resistance of such devices with a transferred film 2 orders of magnitude lower than the contact resistance of the film grown directly. Well, now in the last 4 minutes, I come to the, the description actually of a very simple device which we realized to study. We combined in such field effect device with a pentacene and molybdenum disulfide as channel these 2 materials. Very briefly, in this project we also developed the growth of molybdenum disulfide, introducing in the CVD reactor so-called Knudsen cell for the precursors, which results in much higher reproducibility of the growth of TMDs. This is, for example, 10 by 10, about 10 by 10 millimeter layer of silicon oxide, where only nearly monolayer crystals of molybdenum disulfide were grown with very little inclusions of multi-layers. And finally, this is the device characteristic. This is very fresh measurements. This is very preliminary data, but you actually, from such a device construction with 2 channels, with pentacene channel of P-type and molybdenum disulfide channel of N-type, you produce a device showing a very clear ambipolar behavior actually as we expect this. It's very interesting that we recently started to study the photoresponse of these devices to the white light, and we see strong enhancement of this heterostructure device in comparison to the bare molybdenum disulfide device, and now we are working on understanding the origin of this enhancement. With this, I would like to sum up my talk. This is actually what I introduced you, and introduced you a novel 2D material, organic semiconductor nanosheets, which can be prepared for purpose with specific electronic properties by this electron beam-induced stabilization, and we hope that the sheets can be very useful in variety of heterostructure devices based on different 2D materials. Last but not least, next year, 30th of May, 1st of June, we organize in Jena an annual meeting of German Physical Chemical Society. This is a meeting with about 1,700 participants, and the topic of this year meeting is functional materials, and there will be a focused session on 2D materials. We expect up to 100 people participating. I wish I can welcome you next year in Jena.
Thank you, Andrei. Very, very interesting structures. And now we can turn on the lights, and we open the field for the questions. Any question? Well, I have a question. I have a question in general on how versatile is this technique, because it seems that you can really trap in your layers lots of conducting or semiconducting materials and then transfer it around. What is the limit? How big or how delicate, how robust should be to be transferred without being teared apart anyhow? Because the target material will be weaker than your carbon nanomembranes.
The limits of this method, first of all, the limits to produce carbon nanomembranes, with which molecular precursors it's working. It's working with aromatic precursors, because aromatic precursors are robust on their own, and actually by electron beam irradiation, we only basically induce the cleavage of this carbon-hydrogen bond, but not the aromatic cores. If you, for example, start to apply this technique to aliphatic precursors, you will just damage this aliphatic change and will not be able to make really reasonable material with reasonable structure. How delicate these materials are. Actually, carbon nanomembranes are soft material. They have Young's modulus about 10 gigapascal, but they are very robust from the point of view of handling. It's much easier to handle carbon nanomembranes in comparison to atomic.
Sorry, my question it's evident that the nanomembrane is very robust, but if you try to transport or transfer other materials like molybdenum disulfides or
but we are transferring.
They should be robust as well, or they are sometimes broken down.
They are as they are. We actually, we transfer graphene, we transfer molybdenum disulfide. This is tungsten disulfide, these materials with which we have most of the experience. I cannot say that the handling of this material is much more delicate if you transfer these materials from one solid substrate to another solid substrate. They are much more delicate maybe if you would like to make freestanding structures, completely freestanding. Then it's much easier to work, for example, with these polymer-like materials in comparison to this single crystalline material. This is where I see maybe the main difference.
Okay. Okay, maybe, I don't know if there is another question from the audience. Well, if not, let's thank Andrea again.
Yeah, thank you very much.
Thank you. We move to the last speaker of this session, which is Raquel Lawrence Giralt. And the title of the topic is Efficient CO2 Capture and Oil-Water Separation by Innovative Adsorbents based on modified graphene structures.
Like Madonna. Okay.
Es que no se ve en pantalla. Se desconfigura. ¿Me lo puedes dar? Vale, vale. Bien, entendido. No, es que no veo. Tengo que verlo aquí. ¿Sabes? Tengo que duplicar la pantalla. Pero yo no veo aquí. ¿Te importa si no ves aquí?
No, no pasa nada.
No veo.
Pero se pasa.
Es que no veo.
Ponla ahí, no te preocupes. Gracias. Thank you, Vincenzo. Thank you, Ana Maria, for giving me the opportunity to present these results. Well, I have divided my presentation in two parts. One is the use of graphene for CO2 capture, and the other part is for oil-water separation. Let me introduce IMPLAS. IMPLAS is the Technological Plastic Center. We are located in Valencia, in the east coast of Spain. And we have more than 90,000 square meters facilities dedicated to our pilot plants and laboratories. Some images of one of the pilot plants, the laboratories. And well, we work in all the plastic value chains, from synthesis, we work in the polymerization, nanoparticles modification, etc., to the plastic recovery. And graphene to use in CO2 capture is a good opportunity. We have been working in this application in two projects, Horizon 2020 projects. One of these is gramophone, and the other one is Karmov, so I have mixed the results. And well, as you can see here in this slide, the glaciers has been reducing the ice content during the past years. So this is a picture that was taken in 1941, and several years after, you can see that the ice has been reduced a lot. And as you know, this is due to the global temperature increase, and this increase in the global temperature came in parallel with the CO2 emissions. So we have to to provide solution for the CO2 capture. Well, as you know, the concentration is very high up to now. In the past half century, the increase in the temperature is more due to the greenhouse gases. And we know that the 60% of this increase is the contribution is for the CO2. There are technologies that we can use to capture the CO2 and after that to storage in underground in the rocks, but we need to clean and compress the CO2. What are the technologies that up to now we can use? We can separate or capture the CO2 using solvents. That is a conventional technology based on aqueous amines and salts. To use polymeric membranes, solid sorbents, that is about, my talk is about solid sorbents, or to use another process like cryogenic process that but the TRL is very low. Well, this is a picture to show you the different technology, what is the maturity of these technologies, the TRL, but we know that different technologies, we can find some advantages, but a lot of disadvantages, depending on the technique that we are using to capture the CO2. What is the main advantages of the solid sorbents compared with the rest of the technologies that I show in the pictures? One of these is the less energetic cost for the solid sorbents. Another one is the working temperature. We can work up to 700 degrees. And well, if we compare, for example, with membranes, that membranes can be very selective, are clean, the cost is not too high, but the purity is limited. So has to be changed a lot. So only one technology maybe is not the solution. And what can we use? Carbon sorbents based on graphene. Carbon-based materials has low cost, high surface area. We can modulate the structure and the porosity of this material, so we can customize these sorbents in order to obtain the highest effectivity, and we can functionalize these carbon structures. And relatively, the regeneration of this structure is easier compared with another. What is the problem using this type of sorbents? Mainly the relative selectivity and the temperature, but we can solve it doing modulating and functionalizing the surface of these materials. So we can have a lot of opportunities to use in different areas. What is the other advantage that we cannot find in other technologies is the conductivity. Really, when you use this type of materials, we can regenerate the absorbent thanks to the conductivity of the materials. We can heat it using microwave or heating it by Joule effect. So this is a very high advantage for these materials. So let's move on. And well, another possibility is to help to increase the effectivity using polymers together with the carbon structures. So we can use solid sorbents combined with PEI, for example. We can, can activate the surface of the graphene, and after that to functionalize bicovalent bonds with PEI. This is some results in order that you see that when we increase the content of PEI, we increase the capture of the CO2. And also the number of the cycles, when we use this and regenerate the effectivity, we can maintain the effectivity. Sorry. Well, we can also use membranes, doping these membranes with several polymers, like polysulfone, PTM-SP, etc. Well, here we have more information about dopper membranes. Or we can also, not only with polymers, we can also dope these membranes using metal organic frameworks or graphene materials. So all these technologies we have to apply and to work on because, as you know, the objectives for the technology roadmap of carbon capture and storage will be for the future years not to increase the temperature, the global temperature, more than 4 degrees. So what is the objective really to apply these technologies? We have to have the capacity to take 4 millimoles grain and to have technologies with high chemical and thermal resistance. Also, the energy consumption has to be below 1.5 gigajoules per ton, and the cost has to be between 20 and 50 euros per ton. And the cumulative mass in global has to be 120 gigatons of CO2 between 2020 and 2050. So this is a global image of the objectives for different countries. And for example, you can see here that China will be the highest, the country that has to reduce, to capture the higher CO2. What is the solution that we propose? We propose to combine different technologies, solid sorbents and membranes. In Carmov projects, for example, we are using membranes and solid sorbents based on carbon. And in Gramophone project, we are combining metal organic frameworks with graphene oxide aerogels. And we are designing a system where we can regenerate the aerogel with microwave or using Joule effect. So like that, using like a carousel that you can change this system, you can regenerate and to use again in the industry. Because we have here the emissions from the industry, and the idea is to capture this CO2 and to use after that in other applications. Well, it's an image of different graphenes that we have obtained in the project, combined with amines. And we can also combine the metal organic framework with graphene. What is the advantage? The high selectivity, good CO2 capacity, and thermally and chemically be stable. But this type of MOF are not good conductors. So for that reason, we have to combine with graphene. So combining with graphene, we have both all the advantages from each material. And this is the results of the project. Here we have used different metal organic frameworks, and we have obtained well, very high absorption capacities in this case, but this has disadvantage about the water sensibility. So we can use this type of sorbents if we remove previously the water from the system, or we can use that combination where we have a good CO2 absorption, but less sensitivity to the instead of water. And the other application that we have used in this project is to use graphene for oil water separation. very fast. Well, as you know, aerogels, well, you can modulate the structure, the porosity, the surface area, depending on how to obtain this aerogel, how to dry and how to maintain the structure is very important. And well, the pore sizes is also very important to capture the substance that you want. And in that case, we have been studying different processes and different processing conditions and different combinations with ascorbic acid, and we have obtained very good properties. Well, this is an image, SEM images, where you can see the porosity of the structure. And this is better because you can see that really the aerogel is working with the oil. It's absorbing the oil from, separating from the water. And this is, well, the absorption capacity. Our best results up to now is with graphene oxide at Y. You have here the results. And remember that, well, the CO2 capture is very important to mitigate the global problem that we have up to now, but the best solution is to minimize the CO2 emissions from the industrial point of view, from domestic and private sources. And we need a smart solution for CO2 storage. So thank you very much. I'm on time. Yeah.
Thanks very much. Let's see if graphene can save the world.
Yeah.
So now we have time for questions.
Yes?
Sorry, thank you for the talk. I'm just curious, what's the capacity for your CO2 with regards to graphene compared to your other carbon?
Sorry, because I can't hear you properly.
How much capacity can your graphene take, basically, when it comes to CO2 absorption compared to your other carbon solvents? So what's the difference
compared with other carbon solvents?
So
yeah.
How much CO2, I think, in weight over weight for your materials can capture?
Well, I think I have to check this with my colleagues because this work has been developed by one of my colleagues. And comparing with other structures, I think the effectivity is higher because the porosity of the aerogel, the surface that you can obtain really is higher than in other carbon structures. You can modulate this in order to increase the surface, and the capacity of the absorption is really very, very high. But it's not also important the aerogel. Is the combination with other structures, because you are taking the advantage in the selectivity of the combination with metallic organic frameworks. So this combination is that give us better properties compared to another technologies that you are using along the carbon structure.
Sorry, so if I understand you correctly, the highest capacity is not when you use graphene on its own, it's when you mix graphene with something else.
Exactly.
Thank you.
It's the combination.
Did you measure the surface area of the final material in square meters per gram?
I imagine yes. I don't have this data here, but yes, because we are characterizing of the materials. Mm-hmm. If you need this data, I can check and send you.
Okay. Other question? Well, then, if not, I think we can thank our speakers, all the speakers of this fringe
Thank
session.
you.
So it was a wide overview between modeling to different kinds of applications. Now the conference continues with parallel sessions. We have ones on fundamental, applications, synthesis, standardization, human space exploration in the different rooms. Thank you very much.